Hi everybody, I'm Greg McIntosh and I'm a senior lecturer here at Canterbury Christ Church University based in the School of Natural and Applied Sciences. I thought I'd take some time to talk about some of the work I've been doing recently using my relatively newly installed laboratory facilities here at the university. Now, for those of you that have been keeping up with summertime science, you might remember me from last year when I talked about using magnetic particles to track air pollution by measuring petunia samples that were suspended around Canterbury. What I'm going to talk about today is another application of the study of magnetic properties, and I'm going to use it as an excuse to showcase my new magnetometer. So, this is my little corner of the laboratory, and this is my little magnetic laboratory. So I'll quickly walk you through it. So I have one desk with a set of storage units, which at the moment are full of archaeological samples. Now don't worry, I'll come back to these fellas in a little while. But before we get there, I want to quickly talk you through my little magnetic toys, my magnetic instrumentation. So it just occupies the other corner of my little part of the lab. And we'll start off with my magnetic susceptibility meter. So we use this piece to apply a very weak magnetic field to our samples, and the instrument measures essentially how magnetizable those samples are. And we use this information to tell us about the concentration of magnetic particles that might be present in our samples, whether we've got a high concentration or a low concentration, whether they're strongly magnetic or weakly magnetic. Now, once we've finished with our weak fields, we move on to our strong fields. This is an impulse magnetizer, and we use it to apply large and strong magnetic fields to our samples, and we give our samples a permanent magnetization, or what we call a magnetic memory. Now, this magnetic memory gives us additional information about the concentration of magnetic particles that are present in our samples, so it complements the magnetic susceptibility that we previously measured. But it also gives us additional information. We can use that magnetic memory to tell us something about the composition of the magnetic particles themselves. We might have different compositions of magnetic particles that have different properties of their magnetic memories. Now, this is really interesting because we may have a biomonitoring sample that has one population of magnetic particles that are associated with natural processes. But we might have another population of particles that are associated with anthropogenic polluting processes. And we can use our magnetic memory to try and distinguish between them. In a different context, in an archaeological context, we might have one set of particles affected by thermal processes, so when our archaeological remains have been heated. But we might have another set of particles that are affected by weathering, so once those archaeological remains have been abandoned, we might have weathering processes, and again we can use that magnetic memory to try and separate those two effects. So by making use of these magnetic memory effects, we can answer a whole host of really interesting scientific questions. My next bit of kit is an alternating field demagnetizer. Now, this demagnetizer we use to progressively demagnetize the magnetic memory of our samples. And it's particularly important when we're looking at geological samples and archaeological samples, which I'm going to talk about very briefly soon. But before I forget, let's get to my latest and newest addition to my magnetic lab. So this is my magnetometer. So with this magnetometer, we can measure the weak magnetic memories that are preserved by our samples. So it consists of some very sensitive solid state magnetic sensors, and you drop your sample inside the instrument and it will work out the strength and direction of that magnetic memory. So there is my magnetic lab. Weak field, strong field, magnetization, remagnetization, demagnetization, and measuring the magnetic memory. Now, with these four basic bits of kit, we can answer a whole host of interesting magnetic and scientific questions. We can study pollution, air pollution, soil pollution, sediment pollution, river pollution, ocean pollution. We could maybe look at past climate change, looking at sediments and soils. We can answer geological questions about the Earth's magnetic field in the past, how tectonic plates have moved in the past, and we can use it to identify archaeological processes as well. And that's what I'm going to talk about in this last little section of the video. Right then, now that you've been introduced to my little magnetic lab, I thought I'd quickly run through some of the stuff that you can do with it. So we're essentially looking at the magnetic properties of natural systems, rocks, soils, sediments, organisms, plants, whatever that may be, and using the magnetic properties to tell us something that's affected those systems. Looking at climate change, looking at tectonic processes, looking at pollution, looking at archaeological processes. For example, we have a basalt sample. This is an example of a basalt, so a basaltic lava flow. This actually comes from Northern Ireland. It's the same age as the columnar basalts that you find on the Giant's Causeways. We might study rocks like these to study how the tectonic motion of the United Kingdom has changed over time. We might use it to study the properties of the Earth's magnetic field and how that's changed over time. Now that's really important to us because the Earth's magnetic field acts to screen us against cosmic radiation. So knowing how that's changed in the past will help us predict how it will change in the future, and that's going to be very important to us in terms of predicting space weather. What we have here is a iron-rich sulfate sediment formed in acidic environments. This is actually from southwest Spain. And preserved inside of there are trace fossils of biological activity, algal mats and algal streamers. And it's interesting to see if we can look to see if there's a magnetic signal associated with past biological activity. Is there a magnetic signature of past biological activity? And we use this to answer questions about life in extreme environments, highly acidic river system in southwestern Spain. We could look at any other extreme environments, both on the Earth and maybe extraterrestrially. Wherever we're interested in looking for signs of life, can we get additional information by studying the magnetism? And I would suggest that we could. But really, maybe we can look at stuff that's a lot younger. This is a ball of moss, and we use this as a magnetic biomonitor. You might suspend this somewhere in the atmosphere, and it will trap atmospheric particles, and then we can measure the magnetization of those particles, the magnetic memory of those particles, and identify those particles associated with pollution, usually traffic pollution, but any other pollutant source might produce its own magnetic signature. And so we can use any kind of organism that we think might have a magnetic signal that's affected. But really what I want to talk to you about is my archaeological samples. So recently I went to an archaeological dig in Bedfordshire. So this was a discovery that was made when they were developing for some new housing. And they discovered these archaeological remains that spanned the Iron Age through to late Saxon times. This is, for example, an example of a baked clay from a kiln that we found on the site. We suspect it's Saxon in age, and we're hoping to confirm that by looking at the magnetic memory of that baked clay. But what's really exciting as well are these rocks here. So you might think to yourself, oh, well, what's that, Greg? It's just a big lump of rock. It's a big piece of, just a big pebble, right? Well, this pebble was found embedded in the remains of Iron Age fire pits that were excavated at the site. Now, the archaeologists know that it's Iron Age based on the archaeological context, the structures that were found, or the remains of the structures that were found on the site, and the remains of pottery fragments. But we can also use the magnetic memory of these pebbles to confirm that. So the way that works is that these pebbles were embedded in the remains of the fire pits. So these rocks were heated up and cooled down along with the fire pits. Now, when they cooled, they become magnetized in the direction of the Earth's magnetic field at that time. They get this natural magnetic memory associated with that cooling event. And we can use the direction of that magnetic memory to work out when it happened. So how do we do that? So very, very quickly, This was embedded in the remains of the fire pit. So it was there in situ. They excavated the remains. I went along to the site and I put on this dollop of plaster. I made a flat surface, so I know that this surface of plaster is horizontal. Can you see that little line marked on there? That's the direction of the present day magnetic north. So once I've oriented my sample, I take it out, bring it to the lab. Once in the lab, I take this pebble and I cut it into smaller samples so that I can study the magnetic memory of the samples. So there are different ways that we can go about that. We can take that pebble and we can maybe drill a sample from it. So we might get a sample that looks something like this, a cylindrical sample, and we just drill in to those pebbles. Maybe we cut cubes instead. And so depending on how we want to go about this, we can take different ways of getting samples from those pebbles. Because we know where the horizontal was and where the north was in our pebble, we also know the horizontal surface and the direction of north in our sample. This isn't one of the pebbles, by the way. This is an ancient Greek kiln. This comes from an ancient Greek kiln. So this is something like the 2nd or 3rd century BCE from Greece. This is actually from a Roman age kiln from Bulgaria. And because we know the direction of magnetic north, the present day direction north, the present day horizontal, we take these samples and we measure the direction of the magnetic memory that they preserve. And from that information, we can work out when they last cooled. Pretty neat, right? So we can go back to these samples, cut cubes or cylinders from them. We take our samples, we go to our demagnetizer, and we progressively demagnetize the samples. Each time we demagnetize them, we measure what's left of the magnetic memory using our magnetometer. And then once we've completely demagnetized them, we can figure out that bit of the magnetic memory that's associated with the last time that they cooled down. And that bit of the magnetic memory we can use to tell us when that happened. All because of a magnetometer, a demagnetizer, a susceptometer, an impulse magnetizer, a bit of science, and a bit of imagination. Pretty cool, right? All you need is an interesting scientific question that involves magnetism, and we have the laboratory to help you answer that question. So I'll stop there before I pass out with excitement. See you guys soon.